Hello, everyone. My name is Matthew Austin. I'm a senior computational designer at Aurecon, a large engineering consultancy firm in Australia, New Zealand, and Asia. We do a lot of stuff around linear infrastructure where we'll see some kind of examples and some kind of references made to that, so keep that in mind. Other than that, the talk is a case for esoteric types in computational geometry and exploration of the state of geometry kernels in the 21st century. Just a quick shout out to Tristan Morgan, my co-author, before we get started. Thanks for coming out, and let's get going. When you talk about computational geometry, you also implicitly reference some sort of geometry kernel. A geometry kernel is the mathematical principles being implemented in order to be able to produce geometry within a computer, i.e. computational geometry. And therefore, the history of computational geometry is therefore the history of the kernels that it has been written in. And that history is long and varied. Within the history of kernels, some things have been optimized towards certain goals at the cost of others. More specifically, because these kernels are the very thing that enables computer-aided design software, they have been optimized towards improving the user experience of these softwares. In short, this user experience optimization has come in the form of three key priorities. Firstly, being able to do calculations quickly. Secondly, due to its entanglement with computer graphics, being able to visually render the geometry to a pixel array to display back to the user. And thirdly, and most poignantly to this paper, is the minimizing of geometric types, for example, lines, arcs, meshes, NURB surfaces. For example, Rhino 3D, a commonly used modeling software, forgoes ellipses entirely, as NURBS curves are capable of representing them exactly, at the sacrifice of their parametrization. However, although this observation that the user experience of computer-aided design software has had a hand in how geometry kernels have been developed may be of historical interest, in the context of this talk and this paper, it is the premise that this is not the only paradigm in which computational geometry can and should be optimized. The next question we need to ask is what constitutes geometry in any given geometry kernel? And this is a weirdly more fuzzy question than you would first think, that not everything is considered geometry in the same way in every given geometry kernel. And when you start looking into it, you begin to need a particularly broad definition. So ignore the equation on the screen. I'm pretty sure that a lot of you might not be able to understand it, but effectively what is being said is that if I can construct some set of points, like a point cloud or a curve, which is an infinite set of points, or a surface, which is an infinite set of points, or a mesh that has an infinite set of points on it, then that is a super broad definition of what constitutes geometry. And this definition is powerful in its broadness. However, this definition implies that there are an infinite number of possible geometric entities, and those geometric entities need to be hard-coded into the kernel as geometric types, and no geometric kernel will ever have an infinite number of types. And thus, we end up at this point where we have a set of things that are geometric types and a set of things that are considered operations. That, for example, an extrusion operation could be defined as taking a curve and a vector and returning a mesh. However, if extrusion exists as a geometric type, then we can take the exact same curve and vector and produce an extrusion object. In fact, an operation is merely the absence of a geometric type being defined within a kernel. This shouldn't be surprising. The goal of 3D modeling software is to produce these artifacts, and by minimizing the number of types, it also minimizes the number of operations that can be performed. However, while a wide gamut of computer-aided design software have a majority of their underlying types in common, they also introduce specific types based on the disciplinary conventions the software is expected to operate in. For example, transition curves such as clothoids, cubic parabolas, and other types of esoteric curves are commonly used within the civil engineering contexts. Whether it's due to being discipline-specific, traditionally framed as an operation to geometry, or an approximation, this paper will define the typification of these processes as esoteric types. While introducing more types often introduces more complexity into a kernel as there are more cases for calculating intersections, how to apply transformation matrices, and so forth. It also allows for the simplification of many problems as the work done by what is traditionally in operation. For example, on the left we see an offset operation in Rhino in which the output is a NURBS curve that very accurately represents the mathematical result while not necessarily maintaining its parametric relationship, while on the right we see that we can produce a mathematical definition that can be wrapped into a type. This becomes particularly useful in linear infrastructure where everything is usually modeled against a curve traditionally called an alignment, in which every subsequent piece of geometry that is produced is always in relationship to that curve rather than the Cartesian space the curve sits in. The advantage of this approach is that as things being modeled often represent the edges of roads, barriers, and tunnels, and these objects can be tied back to the original alignment and be updated whenever it is. Clearly, civil modeling software already defines these types of geometry as it is convenient for it to do so. The point being made here is that the only thing separating a civil modeling kernel and a non-civil modeling kernel is when something is an operation and when something is a geometric type. Geometry kernels are designed, and this type operation dichotomy is one of the most foundational design decisions that can be made. They limit the user into particular ways of working, they streamline desirable workflows, and make certain workflows difficult or impossible. A very desirable behavior within the architecture, engineering, construction industries is that types can be maintained for drawing and dimensioning as they are interpolated. This is super easy with a line because a line is just an interpolation of 2 points and you always get a line out. But when we attempt to do this with an arc, we get over-restrained and get an elliptical arc. A particular type of behavior and thus esoteric type for this industry would be a way of interpolating arcs such that we always get an arc back. The reason that this interpolation behavior is desirable within the AEC is that it makes a more desirable type of loft within its parameters, which would be primarily used for things like tunnels. What we find is that when we loft something, we end up with a NURBS curve with a set of additional points instead of arcs, and that more points are added in order to get a better approximation. This is in contrast to the possibility where you could manipulate the weight of the point as a way of interpolation. However, the priority is to add more points with weight 1 to get that approximation rather than manipulating the control points in order to allow for it to be exportable into more software. Sadly, it is outside our abilities to rewrite the laws of mathematics, and thus an arc itself is not going to be interpolatable the way that we desire. However, a biarc, a type of stitching together of 2 arcs to approximate the kind of arcing behavior we want, can be. And thus, we can create a sectional profile that takes a polyline as a type of control net, finds the average tangents at those points, and constructs biarcs between them to achieve the exact type of behavior that is desirable for tunnels. The great value here with this approach of understanding a loft as a type is that we can manipulate the rail/alignment, the profiles, the parameters, and the way that things are being interpolated over this entire loft so that we get even greater control. And as design decisions change and things get manipulated, we can always update and manipulate the geometry as it is geometry, whereas if it was an operation, it would bake out some other type of geometry that wouldn't necessarily have the same intelligence to allow us to do that. Returning to the original thesis, which is our geometry kernels have been designed around user experience, we are now in a situation where that is not the only way that they can be designed. With the rise of cloud computing, online rendering, and processing platforms, a new type of software product is being introduced into workflows. This type of product aims to not only introduce version controls similar to that of Git workflows, but also not be constrained by proprietary software, file formats, and difficult APIs, but to be a single solution for interpretability that enables seamless collaboration among interdisciplinary teams. Speckle 2021. However, most importantly, these types of products render computational geometry to screen and are fundamentally detached from the kernels that generate the geometric information to be rendered. For example, Autodesk Navisworks reduces all geometry down to meshes for clash detection, while Speckle provides an easy-to-use visualization tool without any of the tools inbuilt to edit the geometry it visualizes. Thus, in a paradigm where these types of technologies are common, the minimizing of geometric types is not necessarily the only possible goal of computational geometry in the 21st century. Further, the role of printing to screen is done for you as well. To evidence what is being kind of talked about here is a prototype software that was developed that aim was to just be able to get an alignment, put tunnel stuff on it, put road barriers on it, so on and so forth, in order to show an idea. But it is important to this kind of conversation because the rendering and the visualization is being taken care of Speckle for us, and that all the calculation and all the querying is being dealt with a separate kernel. So thus the question becomes, now that geometry kernels do not necessarily need to be optimized to printing to screen, into usability, into being able to show the user what they need quickly, then what can they possibly be optimized for? Thus, as per the question of what constitutes geometry is at the heart of every geometry kernel, and the reasons why something in any given kernel is an operation is not due to some stringent definition of geometry, but disciplinary-oriented decisions about the type of work the kernel is targeting. However, these disciplinary-oriented decisions no longer necessarily offer the same valuable optimizations that they did in the past, as rendering and interpolation products are entering the market, removing the requirement for operations to lower development surface area. This is not to say that the authors are arguing for an all-type encompassing geometry kernel that can do everything imaginable it does, however, miss the underlying point. From a collaborative perspective, where esoteric types may not be available in certain kernels, operations may be successful at drawing these types to screen, but offer significant limitations to collaboration. The crux of this argument is thus not to make a singular geometry kernel, but to throw into question the value of operations as kernels continue developing. For collaboration, it is easier to add a new type than it is to unpick an operation. Currently, the esoteric types being described here are often parametrically constructed by individuals with programming skills with tools such as Grasshopper in order to build out the logic described, as it does not exist in the packages their disciplines use. However, this tends to overcomplicate how simple the esoteric types being described are and make it more difficult for people to collaborate who do not also have programming skills. This is not to say that we necessarily need to inject more types into existing kernels, but that to raise the question how operations have a limiting effect on what is possible. The design decisions made in most commonplace geometry kernels were made 3 to 4 decades ago. Thus, computational geometry is now at an important fulcrum in its history, where its historical axiom and optimizations are now open for criticism. This paper has argued that esoteric types and streamlining their implementation generates positive user experience around cross-disciplinary collaboration, as operations create barriers in what kind of functionality is extendable from a kernel. However, the wider question that should be looked at is, how do we as designers want our kernels to be designed? Sadly, we do not have the answer to the question, but it's a question that needs to be asked. The geometry kernels of the past have been made by computer programmers solving very specific geometric questions. We are now in a position, and computational design is now mature enough, so we can begin to ask, if we were to make geometry kernels specific to our disciplinary requirements, such as the AEC, what would it look like? How can we influence and manipulate that kernel in order to get the best possible outcome? Thank you for listening.